One of the important things about Ikasi is the interaction among the participants and the participants in the lecture. You should really fully exploit that particular situation to come to know your colleagues here. Don't isolate yourself, because you will be losing out by isolating yourself. So that's one of the main aspects of Ikasi, interaction among the participants and lecturers. And it so happens we make the lecturers at least go for lunch with you, so that you can participate in the conversation in the lunch hour too. Okay. And another aspect of Ikasi is that you will get an opportunity to present your work to your colleagues here, and so it so happens it will be organized by two of you, and I would like to have two volunteers from you who would like to organize this, what you call student seminars. And one change we have made in the student seminar, previously it used to go for 30 minutes or 45 minutes, and because so many of you want to give it, the number of minutes has been reduced to 10 minutes, with possibly a question hour of 5 minutes, so that everybody gets opportunity to present their work. Okay. And so I needed two volunteers, and also concerning the program, Ian Stewart and the Logan have organized an excellent program, and Ian is going to talk about the details of the program at the beginning of the second lecture, so that if those who didn't come to the first lecture may miss out on what he has to say. Okay. And now, the first lecturer is
oh boy, okay. I think that may be a little too loud. All right. Okay, well, it's really a great pleasure to be here. This is my second time in Boulder, the first having been when I was a student at CASI in 1997, which is actually when I met Ian, who was at the same CASI with me. Just looking over the agenda for the month. Graham Cribbs was at that CASI. Christian Bauer was at that CASI, and Tim Kate was at that CASI, and I may be missing even, I think that's it from the lectures, but so it was a good year. I'm going to talk about Higgs physics within and beyond the Standard Model. I'm giving 4 lectures this week, and basically I'm going to use the Blackboard, so I'm going to try and get my lecture notes also scanned to put onto this wiki, which I haven't actually seen yet, but hopefully that will be there sometime today or tomorrow. Okay. All right, so let's get started. So my plan is basically to start out with the Higgs mechanism in the Standard Model. Okay. And the relationship between the mass generation of the particles in the Standard Model and the Higgs coupling. I'm going to try and be very pedagogical, just so that I start at the beginning and then you have the groundwork for everything that follows. This is probably going to take all of today's lecture and part of tomorrow's lecture. Then I'm going to give sort of an overview of the collider phenomenology. Of the Standard Model Higgs. Okay. I'm going to touch very, very, very briefly on the PCD corrections. I assume Frank is going to talk a lot more about that. And I'm not really going to talk about the experimental selections. Julia Tom later in the week is an experimentalist, and we'll talk about that, actually, Higgs detection and experimental selections. And then my third topic, so this is going to stretch over 4 lectures, is a couple of examples of Higgs sectors beyond the Standard Model. So extensions of the Standard Model Higgs sector, and I'm going to look at models with 2 Higgs doublets, just to expose you to some of the features that arise when you extend the Higgs sector, model building point of view and also from the phenomenology point of view. And then I'm also going to talk a little bit about models with SU2 triplets, scalars. Okay, and some of the issues that arise when you extend the standard model in that direction. And I encourage you to stop me during the lecture and ask questions, because I'm basically just going to go through till 10:15 and get as far as I get. So it's much better to have kind of a running discussion rather than wait till the end for questions. Okay. All right. Any questions at this point? No. Good. Okay. Okay. So it's going to be interesting using this board. Okay. So the place I want to start is just do a very quick review of the gauge and fermion parts of the standard model Lagrangian. And this will set the stage for the introduction of the standard model Higgs. Okay, by demonstrating the problems with introducing mass terms in the standard model. Okay, so the gauge structure. As you probably all know, there's color is described by SU3 gauge group. I'm not going to talk much about color at all. Okay. The electroweak part of the theory is described by an SU2 left cross U1 hypercharge gauge structure, and I'll go through this in some detail when I introduce the Higgs boson. Okay. So the gauge part of the theory, so what is Maxwell's equations for E and M, is encoded in the Lagrangian in terms of field strength tensors. So the gauge part of the Lagrangian, the 1/4 is the conventional normalization. Here I'll explain what these are. Right? These are the field strength tensors for QCD. Here's the field strength tensors for SU2 left. And then here are the field strength tensors for hypercharge, which is being a U1 doesn't have, so the A here is the gauge index. For SU2 it runs from 1 to 3. For SU3 there are actually 8 generators, so it runs from 1 through 8. And it's just the gauge generator. U1 doesn't have a gauge generator, so B mu is actually gauge invariant. These things are defined as just the usual field strength tensor. If I took just this and wrote it in terms of the electromagnetic gauge, so gauge potential for vector, and then you use the Euler-Lagrange equations to get the equation of motion, what you get is Maxwell's equations in free space. Okay, so that's what this is encoding. For the For the non-abelian groups, I'll just write it down, for example, for color, okay? There's actually an extra term in the field strength tensor, which involves the gauge coupling, depending on your normalization, right? The structure constants of the group, I'll write down what this is in a second. Okay, where
what is G mu A?
Sorry,
not B mu, right? The del mu G mu A.
Oh, no, you're right, absolutely. I was not actually looking at my notes. Okay. Yeah, thank you. And it has to have the same gauge. Every term has to have an A gauge index, so you can tell it's wrong. Okay. Where the structure constants are basically related to the commutation relations of the gauge generators. So I, F, A, B, C, T, C. And for SU2, SU2, which only has 3 gauge generators, FABC are actually just the totally antisymmetric 3-index tensor. So epsilon 1, 2, 3 is equal to 1, and then any interchange of 2 indices picks you up a minus sign, so it's totally antisymmetric. Okay. So these terms here that are bilinear in the gauge fields, when you take this gauge Lagrangian and you multiply everything out, you get terms. So if you just look at the U1 piece, you get essentially just a kinetic term for the gauge field. If you look at the SU3 and SU2 pieces, you get kinetic terms for the gauge fields, but you also get terms that are trilinear and quartic in the gauge couplings, which give rise to the gauge boson self-interactions and the non-abelian theories. So all of that is encoded in this part of the Lagrangian. Okay. So that's part 1. The gauge interactions with matter fields, so fermions and scalar fields, are encoded via the use of covariant derivatives, or the covariant derivative. So in a sense, what I'm doing here is just setting the notation. Okay? The covariant derivative, so basically the idea is if you write down a kinetic term for a scalar field, okay, that transforms under some gauge interaction, when you do the gauge transformation on the field, okay, the kinetic term, the derivatives in the kinetic term will pick up extra pieces from differentiating the gauge transformation. So you have to add some extra stuff to the derivative. I'll write this out in a minute. Okay, involving the gauge fields themselves, so that the whole thing is gauge invariant. And that actually sets the form of the interaction of the gauge fields with the fermions or scalars that are charged under the gauge interaction. So the covariant derivative introduces the gauge coupling strengths for the U1. There's the field. Y is an operator called hypercharge, which I will define in a little while. It's just a charge, but it's not the same as electric charge. Hypercharge and the SU2 left together, once you break down to electromagnetism, the electric charge comes out of that. So we'll see that in more detail later. Here's the SU2 part. G is going to be the gauge coupling of the SU2. PA here are the SU2 generators in whichever basis is appropriate for the field that you're acting on, whichever representation that field is in. For a doublet of SU2, which, is what shows up in the standard model, okay? These generators are the Pauli matrices divided by 2. So just the usual thing. SU2 is the same group that describes spin. Okay. And then for the SU3 part, I'm going to write the strong coupling of GS. And then these are supposed to be the SU3 generators. Okay. And so because Y, TA, and little ta are operators, okay, when they act on a field, you take the appropriate, value, you apply that operator to the field. So, for example, if I have a particle like a lepton, which doesn't carry color, when you apply a color operator to it, you just get 0. Okay, and then so that thing doesn't wind up getting a couple into the gluons. Okay. Oh, and I should just comment that I'm using what is sometimes called the West Coast metric. As opposed to the one that people in GR more often use. And that means that the square of a 4 momentum is equal to the mass squared for a particle if the particle's on shell instead of minus m squared. Anyway, so just so you know. Okay, so I wrote down the gauge covariant derivative. The corresponding gauge transformations are as follows. And I will actually use these, so it's not just academic. So if I have a field say, a matter field, a fermion, or a scalar that transforms under hypercharge, that transformation, the gauge transformation, can be written like this, okay? So essentially, it's just a phase rotation. Y, again, is the hypercharge operator, so that means if I do a gauge transformation and I have, say, two fields with different values of hypercharge, they get rephased by different amounts. Alpha is a scalar function of space and time which describes the gauge transformation. So the transformation on the field, the gauge field, is this usual thing. This is just the normalization of the field. Okay? So the usual thing you remember from electromagnetism, and then what happens to the fermion or the scalar is it gets a phase. Okay. For SU2 left, it's very, very similar. Except now there are three functions of space and time, one for each of the gauge indices. And up here is the gauge generator, again acting on the field. And when you have an exponential of a matrix, it's defined in terms of its Taylor series expansion. So basically you just expand this out. Often we will be dealing only with infinitesimal transformations, and so when you expand this out, you just get 1 plus the stuff in the square brackets acting on psi. Okay. The corresponding gauge transformation to the field looks like what you have in electromagnetism, except there's an extra piece which you need to put in order to have the whole thing work properly. Looking like that. Okay. Okay, and SU3, it looks exactly the same, except replacing this with the SU3 generators and replacing this with the gluon field as appropriate. Okay. So this immediately raises an interesting thing. If I were to say, try to write down a mass term for a gauge boson, okay, a mass term for a gauge boson would look like the following in the Lagrangian. So the Lagrangian would include, okay, as a subset, a term, say for the U1 field. If I wanted to give the hypercharged gauge boson a mass, I'd just write something like that in the Lagrangian. So I'd have this stuff plus that piece. Okay? That term is not gauge invariant, because when you do this gauge transformation, B mu goes to B mu plus this total derivative of an arbitrary scalar field as a function of spacetime, you get some extra junk that shows up here. This term is not gauge invariant. Okay. And that's why all gauge bosons are massless. Right. Yes. Except the W Z.
So the gauge transformation of the gauge field, that equation is true for infinitesimal.
Sorry, say that again?
That equation is true for infinitesimal.
Yeah, this is true. This is the infinitesimal.
Okay.
Or
Which one? The gauge transformation?
you're talking about this one? Actually, it's not true. This part might be only for the infinitesimal. Yeah, okay, yeah. Yeah, I mean, it's this complicated exponential form otherwise, so if you were to write it out as just a one-liner, it's, yeah, in the exponential form it's easier. This is true for general size gauge transformation, but yeah. I mean, we're going to be working basically with infinitesimal gauge transformations pretty much throughout, so that should be good. Okay, so that's the gauge sector. If I push this up too high, I won't be able to pull it down again. But, okay. So what about the Fermion sector? So the standard model contains the following chiral fermion fields. So I'm going to define the fermion fields in terms of left-handed and right-handed states. I'll explain what those are in a second. And we'll see also why you can't write down fermion masses either in the standard model without a Higgs. Okay. So let me write them down and then I'll explain what a chiral fermion is. Okay? So we have 3 copies or generations of the following. Okay? There's a left-handed quark doublet. Okay, which you know, it has a up quark and a down quark. There's the right-handed quarks of these are singlets under SU2. So the way I'm writing this, when I write things as a 2-component little vector here, what I'm implying by that is that it's a doublet under the SU2 transformation. These guys are singlets under the SU2 transformation. All of these things are a triplet of color. Okay. And then for the leptons, there's a left-handed lepton doublet. Okay. There's a right-handed lepton singlet, and no one has ever observed a right-handed neutrino singlet, so I'm not going to write it down. Okay. So that's the lepton sector of the standard, or the fermion sector of the standard model. And when I write the subscript L or R, what I'm doing there is basically using a notation which can be handily represented in terms of 4-component spinors using projection operators. So the chirality projection operators, let me define P left and right, are 1/2, 1. P left is 1 minus gamma 5, P right is 1 plus gamma 5 with a 1/2 in front. Okay? These things have the properties that they project out the left or right chirality states of a fermion, of a 4-component Dirac fermion. If you have a massless fermion, chirality is the same as a property called helicity. Positive helicity, or right-handed helicity, is when the spin of the particle is pointing in the same direction as its momentum. Negative helicity, or left-handed helicity, is when the spin is pointing opposite the momentum. So chirality is sort of a more fundamental, let us say, property than helicity. When the particle has mass, chirality and helicity are not exactly the same, because you can stop the particle, and then which way is its momentum vector pointing, right? So, but you can still have left or right chirality in that case. Well, it's going to be a mixture in that case, right? So, the right projection operator acting on some state is I'm defining this psi right, okay, that way for a fermion, and then similarly for left. Okay. These things are a complete set of operators, so P left plus P right is equal to 1, as you can see really trivially from the definition there. Also, they're projectors, so if you apply it once, you've projected out the right-handed state, say. If you apply it again, nothing is going to happen. You still have the right-handed state. So, they have this property as well. And if you project out, if you project out the right-handed state and then try to project a left-handed state out of that, you get 0. So this and swapped also are 0. Okay. One other quick property that I want to write down. So this is how you define a right or left-handed spinor. For the anti-spinor, okay, psi bar is psi dagger gamma 0. Here I can use the fact that gamma mu and gamma 5 anti-commute to write this as psi dagger. I'm going to pull the P right through the gamma 0. Doing that, the 1 stays as it is. The gamma 5 switches sign, so P right becomes a P left because we pick up that minus sign. Okay? And then I can write this thing P left psi gamma 0 using the fact that gamma phi dagger is equal to gamma phi. Okay? And this is psi bar left. Okay? So basically what I've just, all this math is to show that if you have a psi bar and then a p right on the right-hand side of it, that's a psi left bar. Okay? When they act backwards, you switch the helicity. Okay. Similarly, you could go through this whole procedure using p left, and you just get that state. Okay. Okay, so I'm going to use this to express the Dirac-Lagrangian in terms of chiral states. So the Dirac-Lagrangian, right? Okay. So that would be what you would write down if you wanted to do quantum field theory of a massive particle fermion, okay? Massive Dirac fermion. If you want to describe gauge interactions, you replace this with the covariant derivative, but let me just leave it as little d mu for simplicity here, okay? This first term, I'm in trouble, okay. I'll write it down again. So what I wrote down was, okay, if you just look at the first term, right, I can insert here 1 in the form of p left plus p right. And in fact, I can even write 1 in the form of p left squared plus p right squared, because p left squared is equal to p left, etc. Okay, so let me do that. Okay. And then I separate that into 2 terms. Pull one of these p lefts or p rights through the gamma matrix, which turns into the opposite projector. So there's the p left term, p left squared term. Okay, and you see what I'm going to do now? I'm going to rewrite this as psi bar left, this as psi left, this as psi bar right, and that as psi right. So what we learn is that in the kinetic term of the Dirac-Lagrangian, the chiralities separate. You could write down just a theory of a left-handed chiral fermion, or just a theory of a right-handed chiral fermion, no problem. If this field psi left has a different gauge transformation properties from this field psi right, these terms are still invariant, because you have psi left dagger, psi left. Okay? That is in contrast to the second term, which is the mass term. So if I do the same thing to the mass term, inserting between these two psi's, okay, a 1 in the form of p left squared plus p right squared. Okay, I get that, right? And now, this is going to be a psi bar right, that's going to be a psi bar left, and so on. which is fine as long as psi left and psi right have the same gauge transformation properties. So if you're doing this in just straight QED, everything is good. Okay? If you're doing it straight QCD, everything is good. But if you're including the electroweak interactions where the left-handed and right-handed fermion fields transform differently under SU2 left and hypercharge, these terms are not gauge invariant. So you can't actually write down a mass term for a fermion if its left and right components have different gauge charges. This is what defines the chiral theory. Okay? And then these terms wind up being not gauge invariant. And so you can't write down a mass term for the fermions. This is how it is in the standard model. We wind up not being able to write down a mass term for gauge bosons. Okay, so the W and Z masses, we need to generate them somehow, but we can't just write down a mass term. We can't write down mass terms for the fermions. We know the fermions have mass. We're going to have to generate that somehow. Okay, that sets the stage for the Higgs mechanism. So the Higgs mechanism is the solution to this problem. Yes.
So in both cases, point out that it's not gauge invariant when you put the mass in that way. And should we think of that as a problem just because it won't be renormalizable if we don't have gauge invariant?
That is an excellent question. So this, in a way, is almost a philosophical question. The question is basically, why do we make gauge invariance be our starting axiom? In particle physics, I guess in particle physics, we start from this perspective of first assume the gauge principle and then go for everything else. We don't have to do that, right? So in principle, you could just say, well, let's just write down a non-gauge invariant theory involving a spin 1 boson, okay, and fermions and stuff like that. The issue with gauge invariance is that gauge invariance. So if you just wrote down such a Lagrangian, you have many possible interaction terms. And in principle, if you don't start with the principle of gauge invariance, each one of those, you don't predict them, right? You go and measure each one separately and fill in your theory. With the gauge principle, the theory is very, very tightly predictive. So you essentially have one number, which is the gauge coupling, and then through the Higgs mechanism, the breaking of the gauge symmetry, you have so in the gauge sector, right, you have basically the Higgs vacuum expectation value, which fixes the mass scale for the W and Z bosons. It's an experimentally observed fact that all of those many, many couplings that you would write down, which have no reason to be related to each other without a gauge symmetry, are in fact related to each other in exactly the way you would expect, given a gauge symmetry. So the success of precision electroweak measurements is really pointing in the direction that the gauge principle holds, and down to the per mil level, so including only quantum mechanical corrections. And so the approach that is basically universally taken is that the gauge principle is sacrosanct, and you start from there and then derive everything. It's kind of a matter of predictability. With the gauge principle, you can predict many, many things. Without the gauge principle, they're all just a coincidence. So, yeah, I mean, it's in a way a metaphysical thing, but it's starting from that point has been extremely successful.
What is the relation between gauge invariance and renormalizability?
Yes. If you just wrote down such a theory with a massive spin 1 boson, I think it would not be. Is that true? So, Fourth theory is not a gauge theory. Yeah.
So I don't really know anything other than what I read out of Schmidt, but he does at one point say it turns out that for spin 0 and spin 1/2, you just look at the dimension of the operators, and that gives normalizability. But for spin 1, it turns out you also need gauge invariance. I don't know if he shows this, but the statement is.
Yeah, I mean the operators. I guess it depends which operators you want to write down.
For you,
Yeah.
the longitudinal normally bubbles, I think that's like, so you can have a renormalizable theory when mass is spin one, but for a U1 gauge.
Okay.
It's sort of as if you
Oh,
could
so
not
you're
get
gonna
it.
not be able to- Yeah, that's probably true. I have to look that up. I'm a phenomenologist.
Sorry, just a
Yeah.
follow-up. So then,
Sure.
would it be fair to say that it's really only the precision electroweak data that made us so confident that we would see it Higgs, right? Without that, the motivation would not have been as strong.
I think the motivation would not have been as strong. Yeah, yeah. Again, renormalizability, whether you take renormalizability as an axiom or not, is kind of, again, a metaphysical question. So, yeah, it's certainly nice to have a renormalizable theory, but the theory of neutrino masses is not renormalizable. So, at this point, yes?
From another perspective, is it true that if you want to have masses in one particle, that you must have the
I don't think so, because the rho meson is a massive spin one particle, and it doesn't obey gauge invariance. Rho is massive.
Yeah, that's not masses.
Oh, massless. Oh, I see what you mean. Yeah, because you have to get rid of that extra polarization degree for you. You mean? Yeah, it's probably related to that. Yeah, yeah. Yeah, okay, because it's the reference. Yeah, I think this is true. But for the massive, I mean, the issue isn't the photon. The issue is W and Z, right? The photon is fine as a gauge particle, but if you wanted to make the W and Z some massive spin one random particle that just happens to couple stuff, yeah. Okay, yeah.
So for spin one particle, if it's not gauge, then you may have an interactive problem. You need a constant current to balance the problem. Just like for spin two particle in quantity, you need a anything tensor to solve the interactive problem.
But the conservation of the current is a consequence of the gauge symmetry.
Yes.
Yeah. So it's, yeah. So there's all sorts of problems that come up when you don't have that.
That comes from the unitarity. If you don't have concept current, then there will be an interactive problem in the theory. I guess something like that.
Yeah, it's probably true. Well, I mean, you put dimension 5 operators as well. Yeah, no, this is certainly a problem with massive spin one. But you could always just cook up couplings. If you have no constraint on coupling, you can always just put in what you need, presumably. But it's very contrived in that case. Right? So the whole point of gauge invariance is you have a very simple theory, very constrained, one coupling parameter, and everything comes out. So that's, yeah. Yeah. Well, in that case, it is broken in that case. Yeah. Yeah, no, it's true. I'll probably, I can comment on that when I get to the appropriate point on the Higgs potential. If you crank the Higgs mass up too high, you also run into unitarity problems, but that can actually be traced back to the Higgs self-coupling being too large and being non-perturbative. Okay. Right, so let me now just write down the standard model Higgs mechanism. Okay. So the idea is that we have these issues. We need to generate a mass for the W and Z boson because these are observed to be quite massive. We need to be able to generate masses for fermions despite the fact that their couplings to the weak gauge sector are chiral. Okay? And the way that this is implemented in the standard model is through the Higgs mechanism, which involves introducing a scalar field, which transforms under the gauge symmetries that we want to make massive, okay? And giving it a potential energy function such that the value of that field at the minimum potential energy configuration, so in the vacuum, is non-zero. So the vacuum has stuff in it that carries weak charge, and this is what's responsible for these apparent violations of gauge symmetry, okay, if you don't take into account the vacuum.
So with the vacuum, everything is still gauge invariant. It's just hidden, sometimes people like to say. Okay. So we're going to introduce a SU2 doublet, a scalar field, which I'll call phi. Okay. It's a doublet, so it has two components. I'm going to get ahead of myself a little bit by assigning these electric charges, phi plus and phi 0. We'll see where these come from in a little bit. Each of these things is a complex field. Each of these things is a complex scalar field. Okay. We're going to assign it hypercharge 1/2. That will be responsible for these electric charges, as we'll see later on. And the Lagrangian for such a thing, we're going to have to write some gauge kinetic terms. Okay, using the covariant derivative. The Lagrangian is kinetic minus potential, so a potential energy function, I have to stick a minus sign in front of here. There's going to be a scalar potential. And then there's going to be another piece of the Lagrangian, which I'll write down later, involving the couplings of the scalar field to fermions. Okay, so I'll come to that in a little while. So the first thing I want to look at is the scalar potential. Right? And we can write this down. Basically, once you've defined your scalar field, and if you require gauge invariance and normalizability, the most general scalar potential you can write down is very simple. I'm going to stick a minus sign here for later use. Phi dagger phi is going to be gauge invariant because remember phi transforms by sticking an exponential on the front. And if you do phi dagger, those exponentials kill each other off. So I can write that. Okay, so it's basically like phi to the 4th theory, except the scalar field transforms under SU2 as well. Okay. If both of these coefficients are positive, okay, then the potential looks like this. Okay? So the minimum is at 0, and as you go away from 0, your potential energy goes up, and so, okay, that's fine. Right? This magnitude of phi is just phi over phi. Okay. So the minimum is at phi equals 0. The vacuum is invariant under transformations in SU2 cross U1, because if you take 0 and you apply a phase rotation to it, it's still 0. Okay? If minus mu squared is negative, and lambda is positive, okay, you get a potential. You get a potential which looks like the following. Near the origin, where the phi squared term dominates, the curvature is negative. But further away from the origin, where the phi to the 4th term starts to take over, the curvature comes back up. Okay. So it's going to look like that. Again, here's magnitude of phi. And in this case, the minimum is going to be somewhere here or somewhere here. Okay. At a field value which is non-zero. Okay? And so the vacuum, meaning the minimum energy state of the theory, is actually not invariant under gauge transformations, because if you take a field value which is non-zero and apply a phase rotation to it, you get something which is not the same as what you started with. Okay? To sort of show this more clearly, let me actually write out. In terms of 4 real components, and kind of illustrate these transformation properties. So phi contains 2 complex scalar fields. 2 complex scalar fields can be written in terms of 4 real scalar fields, just the real and imaginary components. So if I write phi like this, the 1/(r) too is because for real scalar fields, you want that 1/2 in front of the kinetic term for canonical normalization. Whereas for complex scalar fields, you don't have that. Okay? And that means, so if I write it like this, then phi dagger phi is actually the sum of the squares of all 4 of these real scalar fields. So it's just phi 1 squared plus phi 2 squared, etc. Okay? So if you take that potential and rewrite it in terms of this, you can think of this as the length of a vector in a 4-dimensional Euclidean space. Okay? And the potential basically tells you, the minimization of the potential tells you that the value of phi dagger phi, if I take that potential and just differentiate with respect to phi dagger phi and find the minimum, okay? The minimum is going to be at phi dagger phi equals mu squared over 2 lambda. Here I'm assuming that mu squared is a positive number, so minus mu squared is negative, so I get that so-called Mexican hat potential in the second picture up there. Okay, this is a positive number. Right? So what this does is it tells you that the minimum corresponds to this four-dimensional vector being a certain length, which is non-zero. Okay, so if you think about 4-dimensional space with vectors in it, this condition is going to pick out a 3-dimensional sphere in that 4-dimensional space, okay? Which is the sphere of minima, the sphere of degenerate minima, okay? So it picks out a sphere in 4 dimensions, and then the SU2 and U1 gauge transformations. So this picks out a sphere. This set of gauge transformation actually corresponds to rotations in this 4-dimensional space, because the gauge transformations basically transform phi 3 into phi 4, phi 1 into phi 2, a phase rotation, or these guys down here into these guys up there, an SU2 rotation, right? So gauge transformations correspond to rotations in this 4-dimensional space. If you rotate in this 4-dimensional space, and you start on that vacuum surface, you'll end up also in just another place on the vacuum surface, right? So SU2 cross U1 gauge transformations don't change the fact that you're at the minimum of the potential. They just change where you are in field space on that surface of minimum. Okay. So the potential is invariant, right? So making a gauge transformation doesn't change the value of the potential, but the particular vacuum state, so a particular vector in that pore space, is not invariant because it gets transformed. Okay. Right, so those guys just rotate you in this space. And in particular, excitation, so if you're sitting somewhere on that minimum, excitations, so oscillations, in the 3 rotational directions that correspond to these gauge transformations cost 0 energy. So basically, excitations in those directions are going to be massless. Okay? The name given to these is Goldstone bosons. Right? And then the excitation in the radial direction, so if you change the length of this vector, you're no longer in the minimum. There's a potential energy barrier in either direction, which is what defines the minimum in the first place. So excitations in the radial direction, of which there's only one, are going to be massive, right? So you get a harmonic oscillator potential, basically, sitting in that minimum. That gives you a massive particle corresponding basically to, if you're sitting down here and you try to oscillate in that direction, the fact that the potential is curved there is going to give you some, it's going to cost you energy to excite in that potential. Right? So this is very generic, right? So if I write this out explicitly, So if I write out the potential explicitly in terms of these four components, why am I doing this? Yeah, okay. This is the 1/2 squared. Okay, right? We're free to choose the basis of phi 1, phi 2, phi 3, phi 4, however we like, relative to the local vacuum value. So pick some point in space-time. At that point in space-time, the field configuration is going to be a certain field configuration at the minimum. Okay. At that point in space-time, we can define our axes, phi 1, phi 2, phi 3, phi 4, however we like. Okay? In particular, we're free to choose a basis, however we like. We can choose a basis so that of phi 1, phi 2, phi 3, phi 4, so that the vacuum expectation value of phi 3, the vacuum value, okay, is equal to some number. Okay, which is this from the minimization condition, okay? And the other three are 0. And I'm picking phi 3 for reasons of tradition, basically, okay? So we're free to choose that at some particular given point in space-time, say the origin of the universe, right? Coordinate point 0. And then I'll say what happens at other points in space-time in a second, okay? So at this point in space-time, we can rewrite phi 3, okay, which remember is a fluctuating field, it's a function of the space-time. Okay? I can write it as this V, the vacuum value, plus excitations about that vacuum value, which I'll call little h, okay? Where the expectation value of little h is 0. Okay? So now h is going to be my oscillating field, and V is just the vacuum about which it's oscillating. Okay. So if I rewrite phi, okay, I1 plus I phi 2, H plus V plus I phi 4, okay, phi 1, phi 2, and phi 4 in this basis correspond to the directions in which the potential is still flat. Okay? And H, fluctuations of H, correspond to this radial direction because I've chosen the radial direction to be the direction of phi 3. Okay? So if you do this and plug it into the potential and look at what you wind up with, so taking this thing, plugging in for phi 3, this H plus V, and then squaring it out. Okay? What you wind up with is once you look at the values of mu squared, lambda, and V in terms of mu squared and lambda and do that multiplication, you wind up getting cancellations between the first term and the second term, such that the coefficient of phi 1 squared is 0. The coefficient of phi 2 squared is 0. Okay? The coefficient of phi 3 squared, or actually H, because I'm plugging in, okay, is lambda V squared. Okay? The coefficient of phi 4 squared is 0, and then there's cubic and quartic terms which are non-zero. So this just corresponds to what I was saying before. If you have excitations in the flat direction of the potential, they cost you 0 energy to make that excitation. The corresponding mass of the particle is 0. If you excite in the radial direction, it costs you energy. That particle has a non-zero mass, essentially. Okay, so these three guys are massless. This thing H is massive with a mass because it's a real field. In the potential, this term corresponds to 1/2 m squared times h squared. Okay, so the mass of this field is going to be 2 times lambda V squared. Okay, right. So that's fine. So this is going to be the Higgs mass in terms of the quartic coupling and the scalar potential. Okay, so that's put all my chalk on the other tray. things in a sort of a Cartesian basis, there's another way that you can express this scalar doublet, at least in terms of infinitesimal excitation, field excitations, which is convenient for another reason. This sort of chalkboard, right? So we can rewrite phi in another convenient form as follows. This is going to be a function of space-time. Right? So I could write it like that. Right? So why do this? Okay, so in this two-component thing, I've actually thrown away phi 1, phi 2, and phi 4, and instead written some functions xi, 1, 2, 3, which, if you take this thing and you act it on this doublet, expanding out just to linear order, this thing will actually repopulate the phi 1, phi 2, and phi 4 components of our original doublet. So the x's you can think of as just another parameterization of those components. The nice thing about this is that the exponential form really corresponds to rotations, right? These are the gauge rotations, in essence. And so it will follow that minimum surface around, as opposed to just going off in a straight line. Okay. So why is this nice? This is nice because, look at the gauge transformations. The hypercharge of our doublet is 1/2. Okay. These are just the Pauli matrices times phi. Okay. And so if we are clever and choose ourselves a gauge such that So we take our original field, which is different at every point in space and time, and has these your vacuum is aligned differently wherever you are in the universe. If you choose the exact correct gauge transformation at every point in space time, you can actually compensate these fields with these gauge transformation parameters. By just making this choice. And you do this at each point in space-time, and you arrive at a gauge in which your gauge transformation has zeroed out all of those fields, right? So you put yourself into a universally coherent field state where everywhere in space your field is pointing in the same direction, just in the direction of phi 3, right, this original h. Okay? So in this gauge, phi is equal to v plus h, whatever, it doesn't matter which one to write first. So in that gauge, phi is just equal to that, okay? There's only one field in there, h, okay? And these xi fields, or equivalently phi 1, phi 2, and phi 4, have been gauged away, right? So we've gotten rid of them by doing a gauge transformation. You can only get rid of them if the theory is gauged, okay? If the theory isn't gauged, they're still there in the spectrum as massless modes, okay? But if the theory is gauged, you can actually get rid of them. You can absorb them into a gauge transformation, just a choice of gauge. You're always free to work in that gauge. And so in that gauge, these fields are not there. They're just nowhere in the Lagrangian. And so this is perfectly reasonable. They're just not physical fields in that gauge. Okay. This gauge is known as unitarity gauge or unitary gauge. And what the words that are often used is that the Goldstone bosons are eaten by the gauge fields in order to generate the gauge boson masses. Eaten just means you can gauge them away by a gauge transformation, but at the cost of putting your gauge sector into a particular gauge. Okay, so you're working that particular gauge. We could have gauged away, so notice the U1Y gauge transformation is just a phase rotation, so it would it would let you get rid of a phi 4, an I times phi 4 if you wanted to. This had the alpha 3 component. Sigma 3 is the third Pauli matrix, 1 minus 1, okay? So this also lets you get rid of a phi 4 if you have a phi 4. So in fact, an appropriate linear combination of a U1Y and an SU2 left gauge transformation would also work to get rid of phi 4. So you can always choose some linear combination to do that. Okay. And then the physical state H is always in the same direction as V, the vacuum expectation value. Okay. All right, so that's the potential and a little bit of the gauge properties. Now let me look at the gauge kinetic term and what comes out of this. Okay. So the gauge kinetic term what we had was the following. So the Lagrangian is a superset of terms, including this one. Okay. Acting on the field phi, which has hypercharge 1/2, and generators of just the Pauli matrices over 2 because it's an SU2 doublet. Oh, and let me just write down the Pauli matrices here for convenience. Okay. So acting on phi, the covariant derivative is d mu and then the 1/2s come in from this 1/2 and that divided by 2. Okay, so there's the covariant derivative. And when I apply this thing to phi, okay, I can actually take these derivatives, apply them to this form of phi. I'm going to work in the gauge where the Goldstone bosons are gone, okay, just because it's so much simpler. Let's pull the 1 over root 2 out front. What you get down here, so the derivative here, V is a number, it's a constant, okay? H is a function of space and time. So the derivative is only going to act on H. Okay? But the other terms will involve H and V, all right? So if you take the the Pauli matrices and stick them in, sigma 3 is going to result in this H plus V staying in the lower components. But sigma 1 and sigma 2 acting on this will pop something up into the upper component of the doublet. And so I can rewrite this thing in the following form. There's the part from hypercharge. G, only the third component, the third Pauli matrix winds up giving you something down there. All this is multiplying H plus V, okay? And in the upper components, we get an I minus I G over 2, because only the W has an off-diagonal Pauli matrix. W1 minus I W2 H plus V. Okay, so there's this thing is an SU2 doublet, right? I can write it like that, okay? Now I'm going to take this and dot it into its own Hermitian conjugate and write out the kinetic terms. In unitary gauge is equal to the following. Right? So basically, this is a 2-component vector. I'm just going to multiply it to its own Hermitian conjugate. So the first term just gets multiplied by its Hermitian conjugate. The second term gets multiplied by its Hermitian conjugate. And notice that This term has an imaginary part and a real part from the I squared. This term has a real part and an imaginary part. Each one of those just gets squared separately. So the result is a normal kinetic term for little h. Okay. This is this term down here squared. And then the first component squared is actually going to give us the following. And I'm going to leave it in the form of this thing times its Hermitian conjugate for reasons that will become clear very soon. Okay. All of these components of the gauge fields are real in this basis, so I can just write it like that. Okay. Notice that this product I could also write as that. Just the product of the two components. Okay. All right, so let's look at these terms. The third term, I'm going to go in reverse order, just because it's simplest. The third term, okay, I can rewrite using the fact that, so what appears in the original covariant derivative is this combination. Okay? This is equivalent to, actually, do I want to do this? Let me just, yeah, I should just keep it clear. Okay. So if you take what I'm about to write and multiply it out, we'll see that you get exactly this thing on the left-hand side. Right. This combination is 2 times the raising operator, or not the raising operator, 2 times sigma plus, which is that matrix. This combination is 2 times what I'm going to call sigma minus. Okay. The action of these operators is basically you take it, you apply it, it pops something in the upper component down to the lower component, or vice versa. Okay. And if you look at how this is going to show up in an interaction term, if you have a thing multiplying a sigma plus, okay, so just using a quark doublet, it raises the d up, okay? So a term in the Lagrangian with a sigma plus in it, sandwiched between 2 quark doublets, okay, is going to give you a URD. That is a net charge minus 1 combination. If you want to couple it to a charged gauge boson, this is going to couple to the W plus. Right. So essentially what I'm doing is I'm identifying the W plus and the W minus by how they couple to fermions, knowing what the charges of the fermions are supposed to be. So this thing I'm going to identify as a W plus, and I'll need to put some proper normalization. This thing I'm going to identify as the W minus because it does exactly the opposite thing. Okay? And so I can say that this combination here, if I want to write it in this basis of sigma plus and sigma minus, after getting all the root 2's correct for the normalization of the complex W plus and W minus, I can write this as actually root 2 W plus sigma plus W minus sigma minus, okay, where where this thing, this combination here, is actually W plus times root 2, because this thing over root 2 is W plus. Okay. So if I take that and put it back into this third term in the Lagrangian, this term is W plus times root 2. This term is W minus times And that Lagrangian term as a whole, that third term, is just going to be equal to a quarter, because the two root 2's cancel part of the 1/8, g squared h plus v squared w plus w minus. Right? So this is extremely important. If I multiply this out, I'm going to get g squared v squared over 4. Right? This is a mass term for the W boson, with W mass mw squared and g squared v squared over 4. Right? The other things that come out of this are the cross term here is 2h times v. The 2 takes care of one of the 2's in the denominator. I can write hw plus w minus. And then the h squared term just comes along like that. Okay. So what are these? Well, what these are basically a mass term for the W boson and couplings of the W boson to one Higgs boson and two Higgs bosons. Okay. So just draw that pictorially. Yeah.
I guess it's not clear to me how we're using this middle block on the right chalkboard that starts with the words third term. I mean, you can just substitute your definitions and jump from the top to the bottom. Right?
Absolutely, yeah.
Or is this for something we're using later?
So this was basically just figuring out how you write W1 sigma 1 W plus W2 sigma 2 in terms of the charge states. Yeah. I'm really only going to be using it here. It's essentially, I want to provide all the tools that you can rederive this from scratch if you have to. So, yeah. It's not always clear, like, which is W plus and which is W minus and where to put the root 2's and all that stuff. So I just wanted to have it up front. Yeah, so I'm going to do, probably tomorrow I'll do the second term, because I don't have 1 minute. But basically that third term is the W mass term and couplings to Higgs. The second term is going to be the Z boson mass and couplings to Higgs. And then I'll define the photon as well. So this first term here is the W mass term. And from this, we actually learn the value of V. This number actually comes from G Fermi, not from the physical mass of the W for radiative correction reasons. Okay, but that's the usual usual Higgs vacuum expectation value that you see. This term describes couplings of the Higgs to a pair of W bosons. Okay, with the Feynman rule, which you get by just sticking an I and reading it off the Lagrangian. Which I can rewrite in terms of MW like that, squared. Okay? And then this last term is a Higgs WW coupling. The Feynman rule for this has an extra symmetry factor in it because they're two identical Higgs bosons, and when you contract those with your external particles, you get an extra factor of 2. Which again can be rewritten in terms of the W mass and V squared like that. Okay, so I better stop at this point because it's time for coffee. But you can see what I'm going to do. I'm going to do the second term next. That linear combination minus G prime d mu plus G W3 is going to be the Z boson, which is a mixture of hypercharge and the third component of the SU2 left fields. And from that you get the Z and its couplings to the Higgs. And then the photon is the orthogonal combination of those two fields. So I'll finish with that tomorrow.